Okay, so last week we talked about soils, and as promised, we're going to move into a unit where we talk about groundwater. And today, this is kind of a topic that goes along with groundwater. You know, isn't groundwater per se. Sometimes they do this earlier in the semester. I decided to try it at this time now, and that's to talk about mass transport phenomena, which means the conditions at which material moves through the environment, how we quantify it. And you'll see we're going to talk about something called the law of mass action. We'll give some examples of how this works. And this will become super important when we talk about contaminants and natural constituents of groundwater that flow in the subsurface. So this topic isn't really covered in the book. This is pretty much will be the only introduction to it. But continue to read the assignment that I gave last week because it will continue to apply for the next two lectures. Today we're going to talk a little bit about what we call mass balance, which is how we define an area in space where we try to take into account all of the stuff that's there. And we'll talk about the way stuff can move within that space and from that space to its surroundings by a couple of processes, diffusion and advection. We've already talked a little bit about the processes through which chemical or biological or radioactive reaction inside of a space can also be an additional kind of term in this equation. And for today, I'm going to leave that out just to simplify things. But we have talked about this, for instance, when we talked about the biological oxygen demand. And then we'll apply this in a couple of cases to some gas exchange across a water air interface. And then next week, or actually Thursday, we'll continue to use this in groundwater systems. So if you take a step back and you say, all right, we're thinking about an environment, it's got some chemical in it, and we want to know what can happen to that chemical. In the most basic sense, the chemical can stay where it is, unchanged. And there are certain chemicals that do that. They're not reactive in the environment. They don't attach to surfaces. They don't eat gas. They don't do things that would change their concentration to change per se. Or it can be transported somewhere else, and that could be with the flow of the medium that they're in. It could be water, it could be air, it could be soil particles that are being moved along. Or it can be transformed, right? Transformed is sort of by any means biological, chemical, radiological. So we've talked a little bit about this. And so again, I'm not going to focus on it again today, but what we really want to think about is this, right? And so we've talked a little bit about this in the beginning of the semester when we talked about reservoirs and fluxes, and we thought a little bit about volumes of water within reservoirs and things, and the kinds of things that might cause things to change in volume over time, and what the time scales are, the residence time, and so forth. But we want to be more quantitative now with respect to especially this aspect, because that ends up being one of the key features of all action involving contaminants in the environment. So this is another way of expressing what I just said, which is that we have some material that's in a reservoir at some initial time, right? And then time will be stepping forward at some point, but what we want to do is first define what's there at a time, and then we can think about what might happen to that box over time, that reservoir, as things change. And these are the things that from at a single point in time that might affect that material. There's some initial amount that's there, there's some amount that could be added, some that could be removed. And in some environments, we can have both these things happen. If they're not in balance, then we're not in steady state, and the amount of material there can go up or down over time. And then we can also have stuff that's generated in a reservoir and consumed in a reservoir, meaning chemical reactions or biological processes are either consuming or producing something. So this aspect of this is what we call transport. And that's what we call reaction. So this is the law of mass balance. And it's a partial differential. And it says that the partial differential of the concentration of a component in a reservoir at a specific time is equal to two terms. And we're going to go through these terms in gory detail, but this is a term that has a second derivative of concentration with respect to x being the distance in a one-dimensional system of motion, so kind of motion along a line, if you will. And this is a second derivative, and this is a first derivative, a derivative of concentration with respect to x. So this is a concentration gradient, we call it, and this is the first derivative or the slope of a concentration gradient. So the steeper a concentration gradient is, the bigger this number will be, either positive or negative. Now, this term is called diffusivity, and this constant d is a diffusion coefficient. This term is called advection, and this is a velocity term, just how fast is stuff moving. So we'll pull this all apart. And like I say, this is the one-dimensional version. You can write this equation for 2 dimensions, for 3 dimensions, and it gets way more complicated. The concepts are the same, so that's why I choose to talk through it with the 1 dimension, because it's kind of easier, I think, to visualize. So we can write that equation out. Again, this is that same equation. Now, the full law of mass action involves some other things that can happen, the things we've already been mentioning, reaction terms, right? So within our box, our reservoir, change in concentration at time can be affected by diffusion, it can be affected by advection, it can be affected by these chemical reactions. And these are what we call the transport functions, and they involve physical motions of things. So you can say that in another way, like in plain English. You can say the change in storage in a mass in a particular time, it's the amount of mass that's transported in or out, in minus out, obviously, plus the amount that's produced minus the amount that's eliminated. These are the chemical reactions. You can also write this as a rate of change, which is what that equation is, which is over time, the rate of change, or the change in concentration per unit time, is just going to be a mass transport rate and a mass transport rate in and out. These are fluxes. We've talked about these terms before. They're given in units of concentration per time or volume per time or something like that. Plus these production and consumption rates were also given in terms of concentration per time. So obviously, we're interested in these kinds of processes. We want to know how fast is something decomposing, but we're also interested in these things, how fast is something moving in the environment, especially in the case of a contaminant, a highly noxious contaminant that's put into an environment. One of our key questions that we always ask is it going to stay there? And is the concentration going to pretty much not change in time? Or is it going to go down because it's being transported? And where it's being transported to, and what's happening to it while it's being transported? Today, we're going to talk about the 2 main ways things can be transported. And then next time, we'll talk about a little bit more about what happens as we're transporting and we're interacting with other things, like as water flows through the ground, it disperses, it has various other effects that can also affect the chemistry. But for now, we're just going to think about things in a simple kind of one-dimensional universe that is what we call isotropic. So the first part of any kind of environmental scientist approach to understanding something in the environment, whether it's a contaminant or not, is to pick a place that we feel like we can define it very well in terms of how much stuff is there and how much stuff might be coming in or going out. Okay. Geochemists call these reservoirs, environmental scientists oftentimes, or environmental engineers, call them control volume. It means the same thing. It's something you choose, you select. You get to choose on the basis of how big of an area you want to study, how difficult or easy you want to make it in terms of quantifying the input rates and the output rates. As you can imagine, as your control volume gets bigger and bigger, you have to have more control points on it where you understand stuff coming in and out. And so, for instance, in a groundwater setting, you'll often see them drilling wells around a control volume, which is to understand fluxes in and out of that area in the subsurface. So we have to define control volumes because they're the things that allow us to say, what is our initial concentration of something in a reservoir and how is it changing? Sometimes you can make these more ideal than others, just like in the case of reservoirs, sometimes they're not ideal. So you do the best you can. And if there are limitations or uncertainties, then you have to obviously incorporate those into your analysis. So this is an example of a control volume for a relatively small lake and some processes that happened in that lake. And so in this particular case, since the lake isn't too big, it's not like the Great Lakes, it's something that you can handle, you might just make your control volume the whole thing. right? The whole thing, including processes that happen up here at the water-air interface, which includes evaporation, precipitation, and gas exchange, and particles coming in, activities that might happen on the lake that might introduce chemicals, oil coming out of boats, trash coming out of boats, etc. Interactions at the bottom that are happening with sediments. You have inflow coming in from a river. You could also obviously have groundwater inflow. It's not shown on this diagram. Output from a stream, and in this case, there's a single point source of contamination coming out of a pipe. And if presumably the reason we're defining this control line is because we want to understand, well, what's the fate of this stuff in this lake? How long, for instance, does it take before it disperses throughout the entire lake? Is it building up? Is it going to be at hazardous concentrations? Is it going to take a long time to disperse? And it's going to be bad in one area of the lake and another other area of the lake. And this is something that we do by starting out with this control line. This is another control line. This is another kind of scenario we've talked about. We've got a river flowing by, and we've got some, physical process going on that's discharging waste through a pipe into the river, and that river is flowing downstream. And so in this case, the control volume is chosen to be big enough to encompass the processes that allow us to reach some kind of steady state down here. It's a little bit more complicated because we're talking about flow conditions in the river, which might change on various cycles, depending on if there's storms or not. So you try to make this big enough that variations in the seasons don't affect it. And so, for instance, you can see here that the composition is mixing, and then it's mixed, and then you go some point far enough down where at least it's homogeneous, so that if over the course of the year there's water flow in the river, and effectively the mixture point here moves down a little bit, at least we're still in a kind of what we call a steady state condition. But these kinds of conditions, and this is true in the subsurface as well, are a little bit more complicated because of the conditions of flow. And the conditions of flow affect both those terms in that transport equation. Okay, so now we'll take apart the two parts of that law of mass action. The first one is diffusion. Everyone, I'm sure, is familiar with the concept. You've heard about it. It's the thing that you experience when you touch a cold surface with your hot hand, and slowly it starts to warm up. That's because heat is diffusing from cold thing to a warm thing. When we talk about composition, diffusion is a process that happens at a molecular level, right? And the presumption is that for instance, diffusion in a fluid, the fluid is also not moving. When the fluid moves, that's advection. And in many cases, in fact, most cases, both those things are happening. But we have to try and separate out the processes. And we'll look at some pictures of that in a second. But so Fick's law, which is he's the person who came up with the kind of mathematical quantification of diffusion, says that the flux, the amount of stuff coming across a boundary in composition over unit time, and we call a boundary in composition a chemical front, right? Like if you saw two layers and there was a big, strong concentration contrast, we call that a chemical front. It's proportional to the size of the concentration contrast and this constant of diffusion, which is called D. And so it turns out that the constant of diffusion is usually more related to the medium. So for instance, water has a very narrow range of constants of diffusion for certain kinds of chemicals. Like ionic salts have a fairly narrow range of D. Molecular solutes like glucose, they have a different value D. Gases have a different value D, but they're all pretty close, and they're defined by it being water. And they are also temperature dependent, as you can imagine. But anyway, we can look these numbers up in the table. And so in one dimension, this tells us if we have an area of high concentration of something and low concentration, the amount of stuff going per unit time is just going to be this constant, characteristic of the solvent, times this ratio, the first derivative of the concentration with respect to X, which is this chemical concentration contrast. It's a diffusion boundary that is defined by how big is the difference in chemical concentration. Like if we have a situation where we've got two parcels of water that somehow come in contact with each other, one of them has just like a little bit more of some element or some chemical in it than the other, and when they touch, that isn't a high concentration contrast, that's a low concentration contrast. So flux change will be slow. But if we have something that's got a really different value, then flux is going to be high. And you can think about this from the perspective of like Le Chatelier's principle for chemical equilibrium. Chemical equilibrium is trying to establish a smooth concentration where there's no variation between the two things, right? And so that's kind of the end point. There are other processes that can compete with that so that we never reach it. But the main point about diffusion to remember is that the bigger the difference in concentration between our two things, the bigger the rate of change will be, flux being a change in concentration per time. So there's lots of processes that follow Fick's law. There's something that we call molecular diffusion, which is, specifically the example of taking a chemical and watching it disperse by, for instance, Brownian motion into a solution. Like if you took a cup of water and you put one drop of red food dye and you didn't stir it and you added the dye in a way that didn't cause any motion in the body of water, you'd see it slowly move out, and that is diffusion. There's something that we call eddy diffusion, which is a kind of a modified version of this that happens in the environment, and it follows the law, even though it isn't appropriately diffusion per se. It's got small advection currents. The advection currents sort of act in a way over very small length scales that cause things to still disperse by this process. Another process that's Fickian is dispersion by flow in porous media. And this will become really important when we talk about groundwater. So if you have water that's very slowly flowing through a medium with a lot of grains, when the water interacts with those grains, it has to go around it. And if you think about that with millions of grains, ad infinitum, it causes the water to have to keep diverting around the grains. And the chemical gradients that are produced by that process end up following this law. Another thing that can be Fickian, even though it's not diffusion, is bioturbation in sediments. So if we have organisms that are living in sediments and they're kind of stirring up the sediments and affecting the layers, this, unless it's very vigorous, in that case, it wouldn't be Fickian, but you can use Fick's law to apply to that. But we're going to specifically apply it to this process here. Okay, so this is an example of what I was talking about, water flowing through the subsurface through some grains. And so you're looking at kind of a cross section of groundwater flow, and these solid things are grains. And you can see there's different flow paths through here. The A flow path is relatively quick. The B flow path is a little bit more convoluted. The C flow path is a little bit more convoluted. So that depending on the length scale over which this happens, different parcels of water will flow through this porous medium at different rates, and the solute that they are carrying becomes dispersed along the direction of flow, right? The stuff that comes through faster will, what we call breakthrough, show up downstream faster than the stuff that goes through a convoluted pathway. And the spreading out of content is more to do with the nature of the porosity and the interconnectedness of the network, something we call permeability, and these are terms we'll define next time in more detail, than they are about the rate of water flow. And this is why we can use Fick's law to help us understand that dispersion. Okay, so here's the other process we'll call advection. Advection is kind of a simpler thing. It's like the wholesale movement of water with the stuff in it to another place, right? So you got water in a river and it's got some solute in it, and that water flows, whatever, 10 meters in a minute. That is an advection. That is moving of material into or out of our box. And so the advective flux is just the velocity of the medium, like how fast is the water moving or the air or whatever, times the concentration of stuff. And as you can see, we know that these give us fluxes are units of concentration per time. And if we've got a velocity, amount of speed per time and a concentration, which is the thing that we're quantifying, you can see how that reduces. We'll talk about units in a second, but that just reduces to this very simple expression. Now, if we want to look at the change, the first derivative, the change of concentration over time, then it just looks like minus V times the change in concentration over X. Again, this concentration gradient. And we have to be careful to note that this is the simple version for when the velocity is also not a function of X, right? If you have just like a very constant stream of motion, if you had a river that was widening or narrowing so that the water was speeding up as it was going along that distance X, then we would have to have a much more complicated term here because velocity is being treated as a constant with respect to X. Does that make sense? If these are just some ideas of some rates, like groundwater might move 1 to 100 meters a year. So you can think about solutes that are in that groundwater taking that long to move from point A to point B, assuming nothing else is happening. Whereas if we're looking at a stream or a river, you can see that it's 0.1 to a meter per second, right? So we can move a lot more distance in a lot shorter period of time. And therefore, when we talk about contaminants in the subsurface and on the surface, we're thinking about different time scales of advection. Okay, so this is kind of a look at how that advection might work, just to sort of help you visualize it. So this is like, you know, a box, and let's say this box has some, you know, water in it and a variable amount of adding in of red jello powder. So when it's really high, it's really red, and when it's low, it's not very high. And presumably this water's been flowing for a while, and so we get this kind of smooth gradient between our high and low areas. And that gradient, in fact, is something that comes from diffusion. But so if we try to mimic the concentration as, you know, this is concentration and this is X moving in this direction, and we're standing somewhere on this river and it's flowing by us in this direction, then, you know, I couldn't get the gradient to be exactly right. The concentration is up and then it's down and it's up. Just, it doesn't quite match the pattern in the gradient, but hopefully you get the point that at any point, either in time, walking along X along the flow path, we can see differences in concentration because of sort of high and low amounts of stuff in there. Or if we were to stay in X in one place and let this water flow by us, then the concentration is going to change per time. And the way we express this equation is this way: change in concentration over time equals minus the velocity of dc dx. And I'll explain that minus sign sort of on the next slide. So the easiest way to think about the signs in this equation are that they are related to how we define convention. So in convention, we have our X increasing in a positive sense down the flow direction, right? So if water is flowing from this side to that side, X is getting higher as we go down this way. Concentration is obviously going up in this box. And if you're standing on the side of this river at a certain point in time where the water's sweeping by you, and we're in one of these places where the concentration from the perspective of you're sitting here, concentration is going up because this parcel of water is going to move by you, then the reason it's going up is because it's increasing in the negative X direction, right? It's increasing as we go back stream. If we had defined X as positive in this direction, then concentration would be changing going up with X, and we wouldn't need a minus sign, but we need a minus sign elsewhere in the equation to counteract it. But in this case, concentration goes up with minus X, which is why we have this minus sign. It's because of the convention of how X is defined. Now here's another condition where you're standing here and the river is going by you, and you can actually see the concentration is going down as the water flows by you, even though as drawn, concentration is going up in positive X. But from a flux perspective, concentration is negative while X is negative. And so we're going to get a going down in solution. So I have some examples here just to kind of think about these processes of diffusion and advection. So this is a scenario where we're looking down on a box. It's like a river, and we've got a slug of composition. And first it's here at one time, then later that slug of composition is down here, and then another, you know, it's down there. So what do you guys think? Is that diffusion or is that advection? No idea? It's actually advection. The reason it's not diffusion is a spreading out of material on its edges due to motions within the body. This is a physical change where this stuff has physically gone from one place to another over time, and so that makes it advection.
So if there were diffusion, the red box would just be spreading down and not like moving discretely.
Right, you would maybe see it fuzzy on the edges.
Yeah.
Right. So if this were a static, if it were like a drop of something that you put into a lake or a pond or whatever, and you watch it kind of become wiggly on its edges. Okay, so here's another example. This is a river. Here's a concentration of some spot at T0. And then at time 1, it's moved downstream. At time 2, it's moved further downstream. At time 3, it's moved further downstream. And you can see it's spread out. And this is a plot of the concentration of the chemical in that spot over time at these different distances. So for the distance it travels from T0 to T1 is called L1. So you can see that distance here. We've got a high concentration maximum at the center of that spot and a fairly narrow spot. By the time we come down to 2, our spot is more spread out and our concentration is lower. By the time we get to 0.3, our concentration is even lower and our spot is more spread out. So you think this one is diffusion or advection?
Both. Yeah.
Right, you're exactly right. It's both, right? And so does everyone see how that works? I mean, the diffusion, the advection part is the part that's saying, yep, we're moving this thing from here to here to here to here, and that's happening at the velocity of the body of water. The diffusion is, oh, while it's happening, it's spreading out on its edges. And in fact, in this case, it's that kind of diffusion I was talking about called eddy diffusion, which is happening from little swirly currents that are happening on the surface of the water. So, and this is pretty common. But hopefully you can kind of visualize the distinction between what they mean. Advection is like the wholesale motion of stuff from one place to another. It's what's causing things to migrate really rapidly in the environment. Whereas diffusion causes this dispersal of stuff, right? So it may make the concentration, well, it does make the concentration in this case in the area of contamination or chemical go down over time as it moves, but it spreads out over a bigger area. So if this were a really toxic contaminant, diluting it by a factor of 10 may not help you. It may still be very high and over a bigger area, which would be of concern to you, or maybe a substance that isn't that bad, so that dispersal as it advects is diluting it to the point where it doesn't need remediation. So there's a sort of a common approach. Okay, so the next one, it's got a map. It's on the maps on the next page, but I just kind of want to explain it first. So this is something that's happening in the surface ocean just off of Florida. So there's a gas called sulfur hexafluoride. It's a very heavy gas, but it turns out to be very chemically inert. You can stick it in water and it doesn't really react with stuff. And so this stuff is put into the water to sort of watch how it disperses and moves to try and track motions in surface water in the oceans. And so what happened is someone went out, well, a group of people went out and they injected this stuff. It's like a dye, but you can't see it, but chemically you can measure it. Injected it in the water, and then they came back later and looked at where the high concentrations of this stuff were. Okay, so that's on this slide. So it's kind of it's a little bit ugly contour map, but it was the best one I could find. So this is where it was injected, over here at this spot. And this is in kind of longitude versus latitude, right? And then they came back 2 weeks later and measured the concentrations. And so these colors are color-coded by concentration. So purple is the highest concentration, followed by those reds, oranges, and yellows, and then blues are the lowest concentration. So what we find is that the highest concentrations, when it was put into the water, is here, and now it's over here, right? And then along the way, we got this kind of trailing edge of still pretty high concentrations, kind of reds and oranges leading back to it, plus this initial narrow zone of injection has somehow spread to this whole wide area. So is this one diffusion or advection? Oh, right, exactly. I mean, if it were just diffusion of that eddy diffusion type, then all the spread would be happening centered around the area. But the fact that it kind of moved from here to here means that there's a current. And what's interesting about this example is that in a lot of examples, the length scale of advection, like this length scale, is longer than the length scale of diffusion, meaning the whole mass of material moves from place to place faster than it spreads out. It does spread out, but the amount of distance that's covered by the spread is smaller than the amount of distance that's covered by the advection. Whereas in this case, you can see there's this amount of advection, and there's basically from this to that amount of diffusion, they're similar. And this is kind of illustrates that you can find settings where this happens, where the dispersion, the thing that we use Fick's law to explain, can be as great as the advection. Another place that happens and we'll talk about this next time, is in groundwater, a very low permeability substrate. The water's having a really hard time flowing through it very quickly, and it's encountering a lot of grains and it's dispersing. We can see the spreading out happening over short length scales relative to the kind of bulk motion of materials. Yeah, one more of these. So these are oil well fires set after the first Gulf War conflict, whenever that was. I think that was not in the 80s. I think it was in the 80s. Anyway, so just like, you know, there's a fire, there's heat obviously at the bottom here that's causing this plume of material to rise in each one of these cases. And so you can see rising material, and then you can also see that the sky itself looks full of particles. So this is an example that's in air instead of water, but it's still governed by the same mass transport phenomena. So what do you think this one is? So there's some advection for sure, right? Because this stuff, we can see it going up, right? Something's happening. There's parcels of air that are being heated up. I think I heard a bolt in there, which is also right, because so whereas we have these big plumes coming up and they're pretty focused here, they start to spread out at their tops and they're causing all this particulate in the atmosphere. That's diffusion. That's happening, you know, over a longer time and length scale, so that when we use the diffusion advection equation, we understand, well, how long does it take for particles to be at an unhealthy concentration, you know, whatever, 5 kilometers away where people are. You need to quantify both of these two things. And, you know, in this case, you can also see these plumes are being bent over by the wind. That adds an additional term of convection, right? So if they were going straight up, that would imply that there's no flow in the body of fluid, the air that they're being injected into. But the fact that this stuff is rising and spreading out and is being pushed over means that we have multiple terms to our advection. We couldn't use a one-dimensional equation. Okay, so this just to remind you again, this is what that equation is. And this is how we quantify the change in concentration of a chemical over time. That's what diffusion looks like. That's what advection looks like. Both of them require us to know in our control volume the relative change in concentration in distance along the direction of flow. And like I say, if you have, excuse me, if your flow is three-dimensional, then you have to have terms that have this, you know, with respect to X, Y, and Z. It gets a lot more complicated, but nevertheless, it can be done. So we use this equation to study all sorts of stuff. For instance, we can look at sediment in sediment pore waters, which we've talked a little bit about already with respect to redox ladder chemistry and so forth. Look at the variation in composition with depth. It turns out that unless the water is completely static and the porosity is very low, meaning the space between the grains, that we're either going to have some flow of water up or down through those sediments. Like think about tidal forcing if they were ocean sediments. It can pump water in and out. That would be described by this. We also have, like, let's say we're going down with depth and all of a sudden we've gone in oxygen. We start to go down the redox ladder. So we start to have, you know, manganese reducing bacteria that are producing manganese 2 plus. And up higher up in the sediments, we don't have that. So all of a sudden we have a chemical contrast, which then sets up diffusion. And so the chemical contrast between having no manganese in solution and having manganese in solution smooths out over time because diffusion wants it to happen. And as I mentioned before, it applies to groundwater flow and river flow and flows in the atmosphere, even if we can't necessarily see them. So this is the full term. And if you recall back to lecture 10, when we were talking about oxygen, biological oxygen demand, I introduced you to the Streeter-Phelps instantaneous oxygen decomposition model to test whether or not a certain waste stream would cause water that was being exposed to the waste stream to go anoxic or not. And we said, oh, you know, that's kind of unrealistic. Usually we use a first order rate term. And I introduced this equation. I said, today we're going to talk about this. And next time we'll talk about this, or later in the semester. So this is how those two things go together. That the reaction terms, which we've already talked about, are internalized to our control volume. They have to do with phenomena, whether they're chemical or biological or radiological, that are happening within our volume. Whereas this term is more of a term that's related to, this is the advection term, obviously, how fast is the water flowing by compared to the rate at which the input of contaminant is. Now, this is another reaction term, which is, as we talked about before, was a re-aeration term, right? If you got water flowing in a river, it can mix with the atmosphere, and this can allow equilibration of gases. It doesn't even have to just be oxygen. It could be, chemical contaminants as well. We'll have an example of this near the end today. But we wrote this equation out, which told us the oxygen at a certain time was the amount of saturation, which is, what exchange with the atmosphere is trying to do, minus the reaction terms, which look like that. And so that's a version of the diffusion advection equation. What's missing from here is diffusion, because in this particular case, the amount of diffusion that happens is small compared to the fundamental process that we're studying. You could add it in there, but it's just, wouldn't change the result. So this is the way you think about this equation from a control volume perspective that's in a box, an equal sized box of infinitesimally small dx. I've just written it as a delta x. But basically, the change in concentration over time is the change in flux over distance, okay? And the change in flux, right, over distance is a way of saying flux is obviously a change in concentration per time, but if we see the change in concentration per time varying as we move through our box, then there has to be some series of processes, either diffusion, advection, or chemical reaction terms that are consuming that. And it also has that negative sign because of the convention of the direction of flow. And, this is just another way of rationalizing that minus sign, which is that if you think about it, if you were in a box and the flux in of something were less than the flux out of something, right? So you got a box here, and the flux out is higher than the flux in. What should happen to our stuff in the box? It should go down, right? So that's kind of why there's a minus sign. If the flux coming in were bigger than the flux going out, then the stuff would go up. But since our flux, because our positive x direction is in the opposite direction, we'd have a minus, and we'd have two minuses that would go together that would allow us to then calculate, or the situation where flux out is less than flux in. So, I mean, I think the minus sign actually makes kind of common intuitive sense. And this is just a note about the units that go into that equation, right? So concentration can be defined in all sorts of ways, like moles per liter or whatever. But this is just moles per cubic centimeter, and it's done that way because distances, I'm going to give you distances in the units of centimeters here. It could also be in meters, it could be in, any unit you want, but this is a concentration over time. That's what this is. Changing concentration over time. And this is a flux over distance. So the distance part is pretty easy, that's a centimeter. So fluxes are given in kind of unusual units, which is concentration, not per volume, but per area over time. And so what that area, that centimeter squared really is this face of the box. It's kind of like how much stuff is coming through this face of the box. If this is a 1 by 1 by 1 centimeter box, then it's the amount coming through here over time. Okay, so this is how the units of the two pieces of flux come together, right? So this equation is just the net part of the flux, and this is the part of flux due to transport. So I've taken out the chemical reaction terms again just to make it simple. So an advective flux is a velocity times a concentration, right? So here's our units of flux from the last slide. This is a velocity, and that's a concentration. And we can see that when we multiply this thing through, this centimeters cancels out one of those. That's how it's centimeters squared. The diffusive flux, again, the flux has the same unit as up here. And the way the units work out here is that a change in concentration with respect to x is actually, moles per cubic centimeter per centimeter, right? Because it's a first derivative. So it's got centimeters to the fourth. And that allows us to understand the units of the diffusivity constant, which are centimeters squared per second, which again, tell us about rates of change across a surface like this. And that's how those things are quantified if you look them up. So remember we talked about this Streeter-Phelps thing, and I think this slide is out of place. I think this slide was meant to be, sorry, this slide was meant to be before this slide. So I apologize. I was moving stuff around yesterday and I forgot to move it. So anyway, this is just to remind you of that calculation. Let's look at another calculation, or another, we won't use the calculation, we'll just look at the effect of diffusion and advection, which is kind of the change in concentration patterns with depth in sediments where we're going through a redox front. And just to remind you, conditions of EH or PE change because of the high BOD represented by the sediments and the restricted flow of water into the sediments, which tends to limit reoxygenation. And so as organic matter is being decomposed, we go down the redox ladder. We have chemical changes that happen as we go down the redox ladder that set up concentration gradients, right? And those concentration gradients are going to be a function of how intense is the respiration that's decomposing the organic matter, so therefore how high is the BOD, as well as how much of the oxidants, the chemicals that are being used to break down organic matter, are present, right? Like if you have only a tiny bit of iron in your sediments, as you're going down with depth and you get to the zone where iron reducing takes place, you're not going to produce much iron in solution if there wasn't much iron in the first place. But if there's a lot of iron, then you get a big pulse of iron. Okay, and that produces gradients that then smooth out with depth that look like diffusion profiles. So this is two scenarios. This is the water and the concentration of chemical A in the water increasing this way, and this is B. And then this is a water sediment interface, and this is down in the sediment. So in case A, we have a chemical that's higher in concentration in the sediments than in, higher in the water than in the sediments. In the case of B, we have something that's higher in the sediments than in the water. So this might be something like oxygen, and this might be something like iron 2+. And so when we look down with depth, instead of seeing like a place where the compositional change happens as being a straight line, we see these kind of bent over profiles. Those bent over profiles happen from diffusion. And in fact, we can measure the extent of this contrast by looking at the change in A with respect to X, the change in A over the change in X. That's what this is. And the bigger this value, the bigger the flux, which is causing this smoothing out to happen. And in this case, the flux goes from this down, right? It's trying to erase the concentration gradient. So what's really happening is this chemical change is happening here, but the diffusion is pushing this boundary down. So it's being pulled down into the sediment. And in this case, where we have something that's low in the water and it's being produced in the sediments, like iron 2+, it's being produced somewhere down here. But because we have a change in B, change in B in this direction over a change in X, diffusion is pushing it up through the sediments. So we got a flux that is coming out of the sediments. And this is the process, for instance, you've heard about manganese nodules that we find on the seabed. We make reduced manganese in marine sediments, even though the bottom water is oxygenated, a certain amount of manganese fluxes out of the sediments slowly. It touches the reoxygenated seawater at the sediment water interface, and then the precipitation makes the nodules. It's a really slow process. It takes millions of years to make those things. But if we were to look at the change in concentration of manganese, for instance, with depth, we'd see a profile like this instead of a sharp contrast. So here's some elements that change in their solubility as a function of being oxidized or reduced. We've talked about manganese or iron before. They're part of the redox ladder. But we also have other chemicals that, even though organisms aren't using them to decompose organic matter, they change their solubility as a function of whether they're oxidized or reduced. So this is some examples of elements, uranium, chromium, and rhenium, that when the water is soluble, or is oxidized, they're soluble. But as soon as the water becomes reduced, it becomes insoluble. So if we had some uranium contamination in a place that had a high BOD stream associated with it, so we expect it as soon as it gets into an oxygen-limited environment, it's going to go down the redox ladder and become reduced, then we can tell that our uranium contamination would turn into a solid. It would become immobilized in that environment, which you might consider a good thing, because then you can remediate it out. Same thing with chromium. If you put chromium-6, which is a very toxic oxidized form of chromium, into an environment where it encounters a reduced setting, then becomes insoluble, and it's something that can be removed from the setting. Rhenium is obviously a very precious metal, and so this is a way of recovering rhenium from dispersed environments. And we talked before about sediments, but I just kind of want to remind you of the gist of why this works, or what the manifestation of it is. right? So we could look down with depth into sediments, and here we see sulfate, ammonia, and phosphate. And we see sulfate going down with depth, and that's because of sulfate reduction, right? So if we had on this plot, we don't have it, but if we had sulfide, we'd see sulfide decreasing, and sulfate, excuse me, I'm pointing to the wrong thing. Sulfate is in purple. Sulfate is decreasing and sulfide would be increasing, right? So this is being consumed far down at depth because of the redox ladder. Ammonia is the blue curve. Ammonia is being increased. Ammonia is tracking the decomposition of organic matter that has amines in it. And so as that happens, ammonia gets produced. And so that happens greater and greater at depth. But instead of seeing a sharp contrast, we see this curved profile because there's a flux, a diffusive flux. Also plotted on here is phosphate. It's not color coded, but it's these bars. And the reason phosphate is going down, if you remember back when we talked about eutrophic lakes, I said that in an oxidized setting, phosphorus binds with iron and makes a mineral called vivianite, but down in sediments, that mineral breaks down because the iron gets reduced, and so the phosphorus gets liberated. So all three of these things follow these kind of diffusion paths. If you look over here, you can see the list of elements that might diffuse in one direction or another across the sediment-water interface. So things that diffuse into sediments are oxidizing agents, things that are used on the redox ladder, like oxygen, nitrate, sulfate, etc. Plus some other elements that are consumed in sediments for other reasons, like the formation of carbonate minerals consume some magnesium, the sticking of potassium on the clay particles consumes some potassium. So we tend to see those things fluxing out of the water into the sediments, whereas things that come out of the sediments are the things that are the products, for instance, of the redox ladder, as we talked about over there. So they're always kind of percolating back out. And this can cause the sediment-water interface to have mineral deposits on them that are relatively unusual in composition compared to the water or the sediments, especially if left undisturbed. And there can be biological colonization associated with those things as well. They can be places where a lot of heavy metals accumulate in addition. This is just another plot. I showed you this one earlier in the semester where we have nitrate going down because of nitrate reduction, manganese going up because of manganese oxidation, manganese reduction, and iron going up because of iron reduction. And again, they're not sharp boundaries because diffusion is changing those patterns. But this boundary happens higher in the sediments than this one because it happens at a less low EH condition. It's higher up on the redox ladder. But this is very common to see, and it's not because of advection, it's not because there's water flowing into sediments, it's because of diffusion process. Okay, so this is an example now of looking in the sediments of an estuary, and we've got sort of three things on this diagram. We've got a plot of EH, that's maybe the most straightforward thing. It's kind of high in the upper part of the sediments, and then lower in the lower part of the sediments. This is depth in the sediments a centimeter. Then we've got these open symbols, which is a concentration of stuff in water, iron and manganese, and there's two different symbols. Iron is circles, manganese is triangles. So over here we've got manganese and iron in solution. It's increasing with depth because of the redox ladder, right? So up here, where there's very little of it in the water, the situation is oxidized, as we can see from the EH. We have oxidized iron and manganese, which are not water soluble. We get below where the EH starts to tick up or tick down, and the reduction takes place, and we start to produce iron and manganese. Now you can also look at the solids. They have these solid symbols. That's iron and manganese in the solids. And at depth, they're really low because it's all being dissolved away by redox ladder reactions to produce that. And high up in the sediments, it's a little bit higher, but you see this really unusual peak in the sediments. That is something that accumulates over time. We're looking at a snapshot of conditions. But because diffusion is constantly causing a flux of these dissolved constituents up across this redox block boundary, they get to a little bit higher up to a point where all of a sudden iron and manganese realize, hey, I'm not soluble anymore, so I'm going to precipitate back out. And so they make this very high concentration layer. And if you imagine in a kind of a add a time dimension to this, go away and come back in like 10 years, where you've added more sediment to the top, and this boundary will have migrated up. As this boundary migrates up over time, it sweeps through this, redissolves it, and transports it higher up into the sediment column, continually adding more and more to it. So the longer this goes on, the more intense this pulse can get. And there are other heavy metals that can be associated with this. So in places where we're adding contaminated sediments, and the sediments are not being disrupted by things like dredging or major storms that rip up the top few tens of centimeters of sediment, we can start to accumulate a lot of stuff in these layers. And that's primarily due to diffusion. Okay, so the next example that I want to look at is aeration, which is how oxygen transports across an air-sea or air-water, air-lake interface. And then we'll talk a little bit at the very end about the transfer of volatile organic carbon compounds, what we call VOCs, again, across an air-water interface. Some other stuff that this can be applied to is that's important, but we're not going to talk about today. It's like CO2 across the air-sea interface. That's one of the key parameters in trying to understand CO2 loading on the atmosphere impact on the oceans, as well as the ocean's ability to absorb CO2 out of the atmosphere. So that's an important kind of calculation. This is obviously important for any process where we've got high BOD and we have high respiration and consumption of oxygen, is how fast can oxygen be brought back into the water. And there's all sorts of processes that happen, but when we get to a static situation where we're looking at air transport across a boundary, it becomes a really simple situation of calculating a flux primarily on the basis of Fick's law. And then we talked about that, as I said earlier. Okay, so I want to remind you about Henry's law, right? We can write it in all sorts of different ways. Henry's law has an equilibrium constant, Kh. So the Kh for oxygen in a setting where we've got some water and some atmosphere above it says that the concentration of oxygen in the water, so oxygen that's dissolved in the aqueous form, over the partial pressure of oxygen in the atmosphere above it is a constant. And that constant is temperature dependent, right? So at high temperature, you put less oxygen in the water than at low temperature, but that's Henry's law. You can rearrange Henry's law in all sorts of ways. Like here, I've rearranged it to be, the concentration of oxygen is Henry's law constant over the partial pressure of oxygen, if we were trying to solve for this. Another way to solve for this is to say that let's subtract one side of the equation from the other so that we can say that the amount of oxygen minus the Henry's law constant times the partial pressure of oxygen is 0. And what that means is that we have chemical equilibrium because it equals 0. We're going to see in a second, we can also have conditions where this minus this doesn't equal 0. Okay, it might equal a positive number or it might equal a negative number, depending on if one or the other has too much oxygen for that setting. It turns out that the primary way the gas exchange happens follows Fick's law, and Fick's law says that the bigger the concentration gradient, the change in concentration over X is, the bigger the flux. So when we set up this equation this way, if we're not at equilibrium, if we don't equal 0, the bigger the number here is in an absolute value sense, the bigger it is above 0 or below 0, the bigger the flux is going to be. For the same exact settings, if we have just a little bit of difference from what is predicted by this, we're going to have a low flux. If we have a big difference, then we're going to have a big flux, and it's really that simple. So if you take a scenario where, for instance, we got less oxygen in our water than we would have in the atmosphere, and so we have this kind of inequality, then diffusion will take place across the air-water interface to re-oxygenate, to take this oxygen and put it back into the water to try and erase that. And it happens, at the rate that is proportional to the change in concentration across that boundary. So we can measure air-water interface fluxes, and this is the same units I introduced to you earlier, moles per centimeter squared per second. And so we can say that the flux is going to be, this is that Henry's law equation that at equilibrium equals 0, right? But when it doesn't equal equilibrium, we can put in a constant of proportionality called a K gas exchange, which is basically a diffusion constant. In this particular example, it's not written with the letter D, it's written with a K. Some people call it a piston velocity, but basically that is a term that allows us to predict the exact flux on the basis of how far out of equilibrium these two things really are. And so I have on some scenarios here, right? If the flux is less than 0, right, then there's a flux going from air to water. If you think about distance being defined upward from the water into the air, if the flux is greater than 0, then there's oxygen coming from the water to the air, meaning let's say we got a lot of photosynthesis, we've got overproduction of oxygen, it's going to bleed out into the air. And if flux equals 0, you can put that back into this equation and you can reduce it down, and you see that the K gas exchange in that case just becomes 1, and this whole equation just boils down again to the Henry's law as written on the last slide. So it turns out that the K gas exchange is a little bit more complicated than just a constant of proportionality, because it does depend on the actual conditions in the environment. Stuff like how much wind is there? Is the water flowing? What is the temperature? What is the nature of water flow? So the more complicated, the more turbulent the flow is. I think about a stormy condition where you got lots of waves on the top of the ocean, the more difficult it is to calculate this parameter. We're going to look at a relatively simple scenario where we've just got some static air over some static water, and where we can kind of look up K gas exchange values from a table. So this is a scenario where we've got air and water, and this is the interface between them, okay? And it turns out that gas is exchanging one direction or another. This, would be a flux from the water out, a flux from the air into the water. And right at this boundary, we have a thin film condition where diffusion is the primary role of transport. Meaning, like, even if there's wind up here in the atmosphere, if you get close enough to the water surface, it's like a thin little layer, maybe really small, very small fractions of a millimeter, where the air isn't really moving. Instead, it's kind of more of a static diffusion. And the same thing happens in the water, where there's probably some kind of advection and stirring deeper down in the water that's kind of smoothing out the concentration. But when we get close to the surface, the water motion isn't as much, and so the diffusion is the primary way that gas molecules get from here up to this surface and across. It turns out that in real life situations, this film is pretty small and usually neglected unless you're doing some kind of like chemical engineering thing. And instead, we simplify this to say there's no gas film layer, but there is a water film layer. And so the chemical equilibrium is happening at the point of intersection of the water film that sits on top of the water and the air. And this is the concentration gradient that dC dx in Fick's law, and Fick's law officially applies here. So this is a plot of depth from air into water, and this is concentration increasing in that direction. So the way I've drawn this, we have more oxygen in the air than in the water, and so we're going to re-oxygenate through a process of aeration. We get a smooth profile down here because of infection, which is causing mixing and it's smoothing out the variation. Same thing in the atmosphere. So the diffusion we can predict because we know we have high concentration there, low concentration there, and it's trying to smooth out that the flux is going to be down, and we can write this out as an expression, the flux expression, and I've given the distance x here just in L, length scale, instead of in units x, just to make it simple and not confusing with the gx. And you can kind of calculate what that layer thickness is, or you can measure it in various places. And it turns out it's pretty thin. It's like 1/10 to 2/10 of a millimeter. If you get into situations where you have like a lot of biological activity in a lake and you get what's called a biofilm on top, that can affect the rate of transport, and it changes the gas exchange coefficient, or an oil slick is another thing that can change the gas coefficients. But this is for sort of clean, pure water without any oil sitting on the surface or particles sitting on the surface or anything else. And if there was something there, then those lengths would change. So the very last example is to look at a halogenated hydrocarbon. This is trichloroethylene. That's the molecule of it. It's ethylene. It's got 2 carbons with a double bond in it. Ethylene itself would be, CH2 bonded to CH2 or whatever, C2H4. Trichloroethylene is replacing 3 of those 4 with chlorine. It's a really common industrial solvent. I had a job in high school where we were like dipping our hands in this stuff and cleaning off slides in the biological lab without any air venting, which isn't such a great thing. which we now know. And it actually would take all the fat out of your hand. It was really weird. But in any event, it's used as a solvent to remove grease from metal parts. It's used in adhesives and paint removers. If any of you remember, I've forgotten what it's called, but the liquid paper. This is stuff that you used to like when people wrote things out by hand. It was like this liquid stuff that if you made a mistake, you would paint it on your paper. Spot removers, dry cleaning fluid, that kind of stuff. And so, it's got a lot of neurotoxicity, it's got cardiotoxicity. The primary mechanism of exposure is when you breathe it. You can drink it, and it's also not good for you, but it's worse when you inhale it. And this is what its inhalation toxicity is. And compared to, there are other chemicals that are much higher. We're going to talk about this in a few weeks, what LC means. LC is basically the lethal concentration of a chemical. It means an LC50 is at what concentration do 50% of the members of a population die when exposed to that concentration. And so we normally think about, instead of LC, we think about LDs, which are lethal doses. And I'll go through the differences in those, as I say, in a couple weeks. There are things that are way more toxic than this, okay? But it's still toxic. There's also something called an odor detection threshold, which is, again, an average for humans. Everyone knows, like, dogs have much better senses of smell than we do. But the average human, there are people that actually work this stuff out and say, okay, what's a typical amount that you can smell? And it's about 20 parts per billion. And so this matters, like, for instance, the thing about that train disaster that happened in eastern Ohio, people are talking about smelling something in the air. The chemical that they're smelling in the air doesn't happen to be one of the most toxic chemicals, but they have a very, very low threshold of detection, meaning they can smell it even at very low concentrations. And so naturally people become concerned when they smell something that they don't normally smell. But really the question becomes, is this concentration, what is this relative to that, for instance, for various chemicals? And if by the time you can detect it, it's already toxic concentration, that's a bad situation, right? But if by the time you can smell it, it still has to go up by 100-fold to be toxic, then that's not as bad. And there are some, these are just some snippets of, information. There's also some acceptable concentrations in water. And you can see that, for instance, the World Health Organization and the US EPA set limits, and the US limit is a lot lower than the World Health Organization of how much you can or can't have in water for drinking. These kinds of chemicals are really hard to clean up out of water. We'll talk specifically about cleaning them up on next Tuesday. So I've made it like a really simple scenario. It's like, okay, we got a lake and it's contaminated with trichloroethylene at 1 part per billion per weight. So the EPA says, oh, you can drink that water if it's less than 5. I probably wouldn't. But anyway, you could. And let's say you got a boat that's floating on that lake, or you've got some sensors at the lake air interface. You want to know, well, how much trichloroethylene is coming out of that lake into the atmosphere? And we're going to start with a really simple assumption that initially the atmosphere has no trichloroethylene in it. Obviously, over time, it's going to equilibrate and it will build some up. But just for purposes of this calculation, the flux is going to be this K gas exchange times the concentration of trichloroethylene in the water minus the concentration of trichloroethylene in the air times the Henry's law constant. But since there's 0 in the air, this whole term becomes 0. And in this case, the initial flux coming out is just going to be whatever the K gas exchange coefficient is times the concentration of the water. And so, I've just put in the values of, what is a typical K gas exchange coefficient times the concentration and sort of calculated out how much is coming out per cubic centimeter, which a cubic centimeter isn't a particularly useful unit. You might think like, well, I'm out there on a boat and accumulating the air over some larger volume. So I kind of calculated here over 1,000 seconds would the amount of gas that's coming into that air around your little rowboat be enough? And it wouldn't be, at least not at a lethal dose. So you can try the calculation for yourself if you want. The final thing I went through is just to also ask, well, can we at least smell it? And so to smell it, we have to know, well, how much is building up in the air? So we can no longer assume that the concentration in the air is 0. At some point in time, it's going to build up. So we can get to the other end point, which is equilibrium. Once the air and the lake have completely equilibrated, how much do we have in the air and can we smell it? And so we have to look up the Henry's law constant for trichloroethylene. We have a concentration in the lake, and then we just want to calculate a concentration in the air that's in equilibrium with that. So this is the equation of the Henry's law constant that we use, right? This is given to on the previous slide, and here is 1 part per billion. We have this, so we want to calculate that. And you have to go through all sorts of machinations to change your units. And right, the trichloroethylene is a small component of the total number of molecules or moles of gas in the atmosphere. And the odor detection limit, which is back here on this slide, is given in parts per billion, right? Meaning fractions of the total in weight. And so we have to basically calculate the amount of trichloroethylene relative to all the other gas molecules versus moles, convert them but with their respective molecular weights into moles, and then figure out the amount. And so when I do that, you basically find out that the TCE in the air equals 30 parts per billion in this example, if we are looking at a volume that is, basically 1,000 times as big as the volume of water. That's like a sort of a realistic value, which is something you would definitely be able to smell, right? It's higher than the odor detection limit of 20. Not toxic, but it's below the toxic threshold, but you would smell it. And so all these calculations are kind of ways in which we look at diffusion, advection, and non-equilibrium conditions. And just always remembering that in a lot of cases, we start out with an equilibrium case to tell us what is the maximum concentration contrast we might have. And then because we need that concentration contrast when we're looking at processes that are diffusive, and then apply that as sort of modification by diffusion or modification by advection operates on that concentration contrast to give us something different than chemical equilibrium would predict. Okay, so like I say, next time we're going to talk a lot about groundwater. First, we'll just talk about all the characteristics of flow and what make them. And then we'll think a little bit about how these diffusion and advection scenarios affect the movement of solutes in the subsurface, so that then for a week from today, we're able to talk about contaminants and why we see them at different concentrations in the subsurface. So questions about this content? All right.